Hey folks, my name is Hunor, and in this video I'm going to explain how to simulate ball movement in a maze with JavaScript. This week I came up with a game where you have to tilt a maze till every ball gets to the center area. In order to have somewhat realistic ball movements, I had to revisit some of my physics and mathematics studies, so be warned, this video is more on mathematics than web development. And I'm not going to lie, some parts of this video will be mind-twisting. While creating this game, I had phases when I was just staring at my own source code wondering what is happening. This video has three main parts. We quickly go through how the game layout is created, how to generate wall and ball elements with JavaScript. Then we are going to see how to tilt the maze and how that affects the ball movements, how it accelerates the balls and how it gives them a direction. And finally, we are going to discuss how can we use trigonometry to figure out how the balls should behave once they hit a wall. I will always show the relevant parts of the source code, but if you're more into web development than calculations with trigonometry, then check out my earlier videos on how to make a snake game with plain JavaScript or a bridge building game with HTML canvas. But if you're still here, then first let's see how the layout is built up. Let's start with the layout real quick before we get to the hardcore calculations. In HTML, we have a maze element which is rather empty, and we will populate it with the walls and ball elements with JavaScript. In JavaScript, we have an array with the initial metadata of the balls containing in which row and which column are they at the beginning of the game. Then we map this array to the exact positions on the screen and extend the data with velocity. At first, the velocities are 0, as the balls are stationary. Then we go through each ball one by one and create an HTML item for them with a ball class, and we position them according to our metadata. Elements with the ball class have an absolute position, so here we can simply set the left and the top positions. Then we add the created ball element both to the maze element to show it on the UI, and also add it to an array for further access. As we are going to change the ball positions in our metadata, we are also going to update them on the UI, so we need to have access to these elements. Then we have a bit of CSS here. The only thing might worth mentioning here is that I'm using negative margin so that the position of the ball will represent the center of the ball and not the top left corner of the HTML element. Then we do a similar thing with the walls. We have an array with the wall metadata containing in which row and column does the wall start. Then we map these values into actual UI pixels. Walls also have a length and direction. When I translate this into HTML elements, then I do not set the width and height based on the direction of the wall, but I always set the height of the element to match the length. Then in case it's a horizontal wall, I rotate it with CSS transform. Of course, you can do this the other way as well and set a width and height according to the wall direction, but I implemented it this way. In CSS, there's also a trick to have round wall caps. I'm using the before and after pseudo elements to add the circle to the end and the beginning of the wall. This might be doable without the pseudo elements by setting a border radius on the wall directly, but considering the rotation that might happen on the wall, this seemed like a nice option. So this is how the layout is initially created. Now let's move on and see how can we tilt the maze. We can tilt the maze horizontally and vertically by moving a wheel to a joystick. We can achieve this effect by handling two event listeners, the mouse down and mouse move. When we press the mouse down, we register the initial position of the mouse. Then on every mouse movement, we compare the new mouse position to these initial values. This way, we get a horizontal and vertical delta. If we want to give visual feedback to the player, we can use these values to move the head of the joystick on the UI. We probably want to limit this movement as the joystick should only move within a limited box or circle, and we don't want to completely flip the maze either. I'm using the min and max functions here to set a limit between -15 and +15. Then we can turn this mouse movement into rotation values. We can make it 1-to-1 so that each pixel of mouse movement will result in 1 degree rotation of the maze. But we can also multiply the mouse movement value with a constant to make it more quick or more slow. This constant here basically sets the sensitivity of the joystick. Also note here that the vertical movement gives us the horizontal rotation, and the horizontal movement gives us the vertical rotation. So that's not a mistake there, but things are a bit twisted. Then we can simply map these rotation values to the transform style of the maze element. By default, this would result in an orthographic projection. If we want to have a perspective projection, then we have to set the perspective property in CSS. But be aware that this perspective property has to be set not on the maze element which we turn, but on its parent. And that's it, we have a maze element that we can tilt with a virtual joystick. I don't go any further with 3D transformations in this video, but if you want to know more about it, check out one of my previous videos where I explain how to create a 3D pattern with CSS transform. Now let's see how movement works and how the ball's direction and speed changes as we tilt the maze. As we saw, every ball has a position and velocity. At the beginning, the velocities are 0 as the balls are stationary. But as we tilt the maze, we generate acceleration that changes the velocities. We can tilt the maze horizontally and vertically. As we play the game, the maze is mostly tilted both horizontally and vertically. But we can handle these two axes separately to simplify our calculations. We can break up our velocities into horizontal and vertical components. The vertical component of the velocity will depend on the horizontal rotation of the maze, and the horizontal component of the velocity will depend on the vertical rotation of the maze. The great thing about breaking up velocity into horizontal and vertical components is that now we can calculate them independently. Then when it comes to moving the ball, we apply both of these components and we get diagonal movement. So let's see how one direction works. Now we're looking at the maze sideways. It doesn't matter which side because we can calculate the effect of horizontal tilt and vertical tilt the same way. But let's say we are looking at the maze frontwise. Now let's tilt the plane vertically by 20 degrees. This will change the horizontal component of the ball's velocity. At any given point, gravity is pulling the ball down, but it can move that way as the plane is in the way. But it can go parallel with the plane. To get the value of this movement, we have to calculate how much force does gravity have on the ball in parallel with the slope. We can break up gravity into two components as well, to a component that is in parallel with the slope and to one that is diagonal to it. To see these forces, we can frame gravity in a rectangle where one side is in parallel with the slope. The sum of these two forces equal gravity. If we move by F1 force, then we move by F2 force, then we did the same movement as we would have done by moving with G force. In other words, as gravity equals to the sum of these vectors, we can replace gravity with these two vectors. Now we got two forces. The one in parallel with the plane will be our force moving the ball in the maze, and the one diagonal to the plane we can either ignore or we can use it to calculate friction. In this video, I'm not going to calculate friction though, let's keep things simple. Now let's calculate the value of these forces. To get the length of the sides of this rectangle, we can use trigonometry. The gravity is splitting this rectangle into two right triangles that have the same angle as the slope. We can multiply the sine value of this angle with gravity to get the parallel component of gravity. Gravity in the real world has an exact value, but as we are in a game where we are measuring things in pixels, we can just make up a number that we see fit. The value we get this way is an acceleration. The balls don't go with a constant speed on a slope, but they get faster and faster as they roll down. Here we can see how to calculate this acceleration with every mouse move event. We already talked about the rotation we get from the mouse movement. Now we only add a few lines to turn this rotation into acceleration values. Be aware that trigonometric functions in JavaScript expect radians as inputs. So if we have a rotation in degrees, then first we have to convert them into radians. Then we can use these acceleration values in the main game loop. The main game loop is a request animation frame function that gets called approximately 60 times every second. In this function, we can update the horizontal and vertical velocity components of each ball in every cycle with the acceleration determined by the horizontal and vertical inclination of the plane. With the new velocity values, we can easily calculate the ball's next position and update the ball position on the UI. Here you might also want to limit velocity, because otherwise things get fast quickly. This is a bit of cheating the laws of physics, and with a better model this wouldn't be necessary. But this is a game, so we can make our own rules. And there you go, we have a ball rolling on a plane, continuously changing direction and speed based on the tilt of the maze. But what will happen if they run into a wall? Hitting a wall is simple at first, but then it gets complicated. In the main game loop, in every cycle between calculating the next position of each ball and actually moving them to that position on the UI, we also go through each wall and see if the ball hits any of them. Vertical and horizontal walls behave quite similarly, just the directions are changing. We calculate the starting coordinate and end coordinate for easier calculations, then we test if the ball is about to get too close to them. We are using the future position of the balls here. We calculate where the ball would be next, if it wouldn't bump into a wall, and then we test if that position is okay. First we check if the ball will be within the stripe of the wall. If it will be, that doesn't mean that the ball will hit the wall. The ball could be still before or after it, but if the ball isn't in the stripe of the wall, then it's certainly not gonna hit the wall. Keep in mind that the wall is not just a line, and the ball is not just a point. They have an extent, so when we do this check, we have to take into consideration the width of the wall and the size of the ball. If any parts are overlapping, then we take further inspections. We can break down the possible collision into 3+1 cases. We can hit the main part of the wall, we can hit one or the other wall cap, or the +1 case is when we do not hit the wall is just passing before or after the wall. Let's start with the first case because that's the simple one. If a ball is overlapping with the main part of the wall, then we simply shift the wall back till the ball is just next to the wall. We change the ball's position even before the end of the main loop where we would normally change the ball's position, because this move just has to happen. And we also update the future position of the ball that we use in collision detection because this one is obsolete. Once we dealt with position, we also have to deal with velocity. As we saw, the ball's velocity consists of two components. Conveniently enough, one of these components is always diagonal to the wall. This component has to change as the ball can't move into the wall's direction anymore. There are two options here. We can either just set it to 0 and then the ball just keeps on rolling along the wall, or we can set it to be a proportion of its original value but in the opposite direction. This will result in a bouncy effect. The ball keeps bouncing on the wall till this component ultimately goes down to 0. It might be interesting to note that if we keep up the tilt of the maze, then we still have an acceleration towards the wall. The ball still tries to go through it, but in every cycle we detect the hit, ignore the movement towards the wall, and let it roll along the wall. Now let's get to the second case, hitting the wall cap. Hitting the wall cap is trickier because we can't just simply ignore one component of the velocity and go with the other one. We have to come up with a completely new velocity to simulate the ball rolling over the wall cap. So how can we deal with this? First, we check if the ball will get too close. Maybe it won't, and then we don't have a problem. The distance we are looking for is the one between the center of the ball and the center of the wall cap. If this distance is less than half the size of the ball plus the radius of the wall cap, then we have a hit. We can get this distance with trigonometry. We know the position of the center of the ball, and we know the center of the wall cap as that is the wall's starting point or the wall's endpoint. We frame these 2 points into a right triangle where one side is the difference of the horizontal positions and one side is the difference of the vertical positions. And then we can calculate the distance with the Pythagorean theorem. If the distance is too close, then first we push the ball back to the closest possible position where it would still not overlap with the wall cap. We can do this in 2 steps. First we need to get the angle of the impact with arctangent. Again, we know the vertical and horizontal distances of these 2 points, so we have everything to calculate this angle. Then we do the inverse of this calculation. We use this angle and the distance the ball should be from the wall cap to calculate the horizontal and vertical delta from the center of the wall cap. Then we just add these delta values to the center of the wall cap and we get the new ball position that doesn't overlap with the wall anymore. But this is only half of the solution. The ball still tries to move in the direction of the wall. This situation is somewhat similar to what we had when gravity was pulling the ball down on an inclined plane, but it couldn't go downwards and it had to go in parallel with the plane. But now the surface is not flat, and the force moving the ball doesn't point downwards. Yet for a second we can think of the wall cap as a flat surface and see what will happen. The calculation I'm showing here might not fully represent the laws of physics, so if you are building bridges, please use a more accurate method. But in a game environment like this, it works quite smoothly. So first we imagine that our ball is rolling on a flat surface, so we can break up our force into two components again. One that is in direction of the wall, where the ball can't move anymore, and one that is diagonal to it. The sum of these two forces equal the original velocity, so we can replace velocity with them. The only thing we need to know to calculate these forces is the magnitude of the velocity and the angle between the velocity's direction and the impact's direction. The first is simple. We can use the Pythagorean theorem again to get this value. But to get the angle, we need to calculate two other angles first. First we calculate the angle of impact with the getAngle function we defined before. This is using arctangent under the hood and uses the horizontal and vertical distance between the center of the ball and the wall cap. Then we calculate the heading of the velocity with a similar method. Now that we got these two angles, we can calculate the difference between them. We can subtract the heading of velocity from the angle of impact. Then we get the angle we need to calculate the two components of velocity. Here these two angles have the same value, so we can use trigonometry again to get the velocity component that is diagonal to the impact. The other component that is heading towards the wall we can ignore, as the ball can't move that way. And we can point this diagonal force as our new velocity. But this velocity won't be the result of our calculations. The ball can move this way now, but this force moves the ball away from the wall. Instead of that, we want to have a rolling effect, so we have to pull the ball back towards the wall cap. We more or less do the opposite movement as we did before when we moved the ball away from it, but in a bit different way. We are going to use sine and cosine functions again to get the horizontal and vertical position offsets of the end of the velocity from the center of the wall cap. All we need is the desired distance of the 2 points and the direction this point should be from the center of the wall cap. The distance we know, it should be half the size of the ball and the radius of the wall cap. And the angle we can also figure out, as it should be under the same angle as the current end of the velocity from the wall cap. So let's find out to what direction our new velocity is heading from the wall cap. It would be easy if we would know to what exact point the velocity is pointing at, but we only know its magnitude, so we have to find another way. Here we see another right triangle, where we know two sides. One side is the closest possible distance between the ball and the wall cap, and one is our latest velocity that is diagonal to the impact. We can use arctangent again to get the angle of this triangle. The angle we get here in this exact example will be a negative value, which will be important in a second. But this is not the angle we wanted, but the one next to it. One other angle we know is the angle of the impact. If we add 108 degrees to the angle of impact, then subtract the rotation we calculated before, then we get an angle that we can use to calculate the horizontal and vertical distance from the center of the wall cap to the end of our new velocity vector. The subtraction here might be confusing a bit, because on the slide it looks like we are adding it together, but remember the rotation we have calculated has resulted in a negative value, and double negative will end up as a plus. So with this angle we can use sine and cosine again to get the horizontal and vertical offset of the endpoint of our new and final velocity vector. We add these delta values to the center of the wall cap and we get the endpoint of our new velocity. Then we make it relative to our new ball position and we get our new velocity. And this is where we end. We get a new ball position and a new velocity that will move the ball to a position that still doesn't overlap with the wall. Keep in mind, as I said before, that this is not an accurate model of how objects roll on other objects. Honestly, I'm not an expert in the field, but it seems to me as a close enough approximation in a game like this. So that's what I wanted to say about this game. If you want to dig deeper, you can find the source code along with the whole game at the links below on CodePen. And I know that this was a lot of math. Next time I promise I do something that's closer to web development. One quick video idea I have is handling device motion to move the ball in the maze. You can use the gyroscope of your phone as user input, and this game would be a perfect fit for that. Or maybe my next video will be something completely different. So please subscribe and let's find out together. See you at the next one.